Thanks, Carol. So my name is Schroeder. I'm a cropping systems agronomist and plant pathologist with the University of Idaho. And a large portion of my research program over the past 6.5, 7 years has been looking at soil acidification and focusing more on management strategies for dealing with our soil acidity. So Hai-Ying Tao gave a great introduction this morning into soil acidification, why it's occurring, some of the impacts of it. And so I'm going to really focus more on some of the management strategies. So I'm not going to belabor this. I know Hai-Ying mentioned most of this morning, but just to point out the first point here, that aluminum toxicity is one of the primary things that's happening in our soils as they acidify. This is resulting in damage to our plant roots, reduced plant growth, which then affects the above ground part of the plants, reduced vigor, and ultimately reductions in yield. So most of the acidification that we see in this region just looks like a normal plant growing out in the field. You may have acidification occurring, but you're not seeing it. You might have a little bit of yield drag, your pulse crops might not do as well, but there are situations where we're actually starting to see acute acidification where you have these patches occurring out in the field. And unlike a root disease, these patches don't really seem to follow any pattern. You know, if this was a root disease, we might expect, maybe in the lower parts of the field or up a draw, maybe a northern slope, be pretty common for Pythium root rot. But I've seen a number of fields where we have patches that are north slopes, south slopes, tops of hills, bottoms of hills, really no rhyme or reason to why they're occurring. But they'll resemble drought stress, may look like some of the other root diseases like Pythium or Rhizok that we might be more familiar with. But what we're generally going to see is reduced seedling vigor, reduction in the number of tillers in our wheat crops, yellowing and stunted plants. Again, these patches can occur anywhere, but one of the keys with soil acidification is if you suspect you've got acidity, you've got patches showing up in the field, is to go out and take a look at that soil pH, and that can give you kind of an indication of what might be going on. And typically within those patches, the soil pH is going to be substantially lower than outside of those patches. We did a survey, in fact this was a survey actually done by Bob Mahler back in the 1980s looking at soil pH in northern Idaho. And you can see the distribution here. Most of the soil pH was probably at about 5.3 or higher. The majority of them coming in about 5.4 to 5.9 in that top 6 inches. And just a small proportion down here below 5.2, which is where we start really getting concerned, seeing aluminum toxicity and some of these other really negative effects occurring. But fast forward 30 years, Doug Finkelberg and I did a survey, again of northern Idaho, and we saw a dramatic shift downwards in pH to where now 75% of the fields we surveyed had a pH below 5.3. So this is getting a little bit concerning. And we overlay the aluminum concentrations. This is the KCl extractable. This is typically the trivalent aluminum, the most toxic form of aluminum to plants. And at 5.2, we start seeing about 5 parts per million. Increases up to 15 at that 5 to 5.1, and then we start seeing pretty dramatic increases once we start going below 5. And if you think about toxicity, when we start getting anywhere from 5 to 10 parts per million, we are going to start seeing some negative impacts on that plant. It may not be really obvious till you start getting below a pH of 5 and start getting more substantial concentrations of aluminum, but you are going to start seeing some yield reductions. And Tim mentioned this as well, just variability across the landscape. As we start thinking about managing for soil acidification, particularly with liming, there's a lot of variation, and it really doesn't follow any pattern per se. This particular 100-acre field that Tabitha Brown had surveyed had pHs ranging from 4.7 up to 6.4. So there's parts of that field that definitely probably need 3 tons of lime. There's other parts of the field that don't need any lime at all. But trying to figure out how we're going to manage the acidification across these landscapes, whether we're going to go do grid sampling for pH, look at our yield maps would be one way you could potentially get at that, using an indicator crop perhaps, something that's not super sensitive but has some sensitivity to lime, just some things we need to think about going forward. Crop tolerance was mentioned. This is one strategy we currently have, and this just kind of ranks the crops that we grow in this area based on the literature and then my observations of these various crops, working with them over the last 10 to 15 years in acid soils. Triticale is probably one of the most tolerant things we can grow in our soils. Wheat is highly tolerant if we have an aluminum tolerant variety. Timothy hay and bluegrass are pretty tolerant. Canola is fairly tolerant. Of our pulse crops, chickpeas are the most tolerant, and I'll show you an example. I actually don't have the picture with me, but we've got a farm over in Moscow that has a pH of about 4.5. I can't grow peas or lentils on that field, but I can get about 800 pounds of chickpeas off of it. So chickpeas have a little bit more tolerance. Then we get down to wheat. If it's an insensitive variety, mustard's fairly sensitive, barley's more sensitive than wheat, and then our round out with peas and lentils at the bottom, which all of our pulse crops are not only being impacted by the direct effect of aluminum toxicity, but because of those low pHs, our rhizobia populations have been greatly reduced, and so these plants are less, have a lowered ability to fix nitrogen. So I want to talk a little bit about some of the work I've been doing with variety selection. So variety selection in wheat crops as well as liming are the two main things I've been working on over the past few years. So this is just a photo of a sensitive variety on the right, in this case scarlet, a hard red wheat. These are both hard red springs. And then Ellicott, which is a tolerant variety on the left. And the day I went out to this field, unlike a good plant pathologist, I forgot to bring my shovel with me that day. So I couldn't dig plants up. But we had a lot of rain, so I thought, well, I'm going to try to pull some plants out of the ground. So I did that. And you can see this plant on the left has all this, it's just kind of brown. It has all this mud and soil clinging to it because all of the fine root hairs and rootlets are still intact on those plants. So all that soil came up with it. The variety on the right, the root hairs and all the growing points of the root have been damaged by aluminum toxicity. The root hairs and small rootlets are basically gone. You have these thickened roots, greatly reduced ability of those plants to take up water and nutrients, and that's how we start seeing these patches occurring in these really acute areas. But all the soil sloughed off that plant as I pulled it out of the soil. So that just kind of gives you an indication of how it's impacting that fine root structure on these plants. So aluminum tolerance is actually a fairly simple, It's a single gene, so it's something that we could easily breed into our material here in the Northwest. Typically it's some sort of a gene, such as in this case a malate transporter gene, where it basically causes the root tips to excrete malate into the soil solution. That malate will chelate or bind to the free aluminum that's in the soil, preventing that trivalent aluminum, which is toxic to the plants, prevents that from being taken up into the plants. There's been cultivars developed in Oklahoma and Kansas. They've been working on this for several decades, as well as parts of Canada. But it just so happens that through our breeding efforts here in the Northwest, through the locations that we've selected for breeding, for selecting varieties, we've actually inadvertently been selecting for some tolerance in our varieties. So this is a photo, this is a screening site over at our Parker Plant Sciences farm just east of Moscow. We've got a corner of that farm that the pH is about 4 to 4.4 in the top 6 inches. That is really acidic. I mentioned before, if we start getting up above 5, 10, 50 parts per million, we can start seeing some levels of toxicity. This particular field has over 300 parts per million KCl extractable aluminum, so it's very acutely acidic. And you can see in this example here, each of these, they're little two paired rows, about 7 feet long. You've got some of these varieties that are basically dead. And then some that look really healthy, some that are not very happy, but they're still alive. But we've got really good differentials between really tolerant and really sensitive. So what I've done is to screen a lot of our varieties. Most of these have come through the variety testing program at Idaho. We've been having some discussions this fall with Clark Neely, who is taken the role as the variety testing individual here in Washington State University, and we're going to be doing a coordinated effort to make sure all the material coming through my program and his are all screened at this location in Moscow. But we rate everything on a 0 to 5 scale, 0 being about the happiest, healthiest looking plant that you could find in the field, and 5 being a dead plant. So kind of our poster child for aluminum sensitivity is L-tan. That's one of the most sensitive varieties that I've looked at as far as winter wheat's concerned. But you can see, as I've indicated in the blue here, these varieties I would consider to be fairly tolerant. If you're in an area where you know you've got aluminum toxicity, you've got issues with soil acidification, those would be varieties to be looking at growing. And you can see, looking at the names of these, it really doesn't matter the source of the varieties. Some of them are from Lima grain. You've got West bred varieties in here, Oregon varieties, Idaho, Washington. Everybody has some material that has some tolerance to aluminum toxicity. The varieties I'm indicated in yellow here, those are getting near that threshold, and I've arbitrarily put this number of 2.5 in there. When you get to a 3, those plants are still alive, but they're being dramatically impacted. They have very reduced tillering, they're stunted. The 4s and 5s are extremely stunted or dead. So those you definitely want to avoid. So things like Norwest Tandem, Westbred 1376, Bruno Stevens, UI Sparrow, and Eltan are among the most sensitive varieties. We've done the same thing for our hard wheats, and again you can see some varieties are very tolerant, such as Norwest 553, a couple Westbred lines in here, including Arrowhead, a couple intermediate, and I'll note LCS Jet in particular. I know that's probably become one of the most popular hard red wheats in the Northwest because of its yield potential. It does really, really well. But it is a little bit more on the intermediate side. But you move over to things such as LCS Rocket, Keldon, and Silver, they're quite a bit more sensitive. So if you're in areas with acute acidification, those aren't going to do very well. We've also looked at the spring wheats, and we now have 2 years of data, so we're getting a little bit more confident on our ratings here. If we look at the hard red spring wheats first, the one I want to point out first of all is this variety clear on the left, Alum. That was a variety released by Mike Pumphrey here about 3 or 4 years ago, specifically because of its superior tolerance to aluminum toxicity. He had some trials up in Rockford where he was screening some of the early material. This had better tolerance than anything else in his trial. So he released that variety, called it Alum, for aluminum tolerant. But you can see other materials in there, other hard reds, such as Westbred 9518, 9668, that are also very tolerant. A couple that are more intermediate, such as the 9662 and Dane. And then there's a number of lines here that are a lot more sensitive, such as Glee, a number of the Syngenta lines, and then Jefferson and Winchester, which are a couple of my checks for the spring wheat. If we shift over to the soft whites, we find even a little bit better tolerance, and in fact, Seahawk has so far been scoring even better than Alum. So a lot of the more recent releases from WSU and Westbred are quite tolerant, including Seahawk, the Westbred 21 or 6121, 6341, Babe, Tico. We start getting into the clubs. They have a little bit less tolerance. They're kind of more intermediate, so JD and Melba. And then UI Stone Diva and Coachman were all pretty sensitive. And despite the fact that Ryan's bumped up above that intermediate line, I still have it listed as a yellow because in our first year of screening, that variety ranked as a 2. This last year, it was about a 3, 3.5. So I'm not really confident to say that it's a sensitive variety yet, and I'd like to screen it for another couple of years to really know how it's going to perform. So that's kind of what I've got for tolerance. I'm going to continue doing this tolerance screening every year, looking at elite breeding material that's coming through the variety programs as well as varieties we grow in this region, and start publishing some of this information online so it's accessible to all the growers. So I want to talk about some of the liming work I've been doing, and Hai-Ying touched on this, and I just briefly want to reiterate some of what she said. So when we're liming, we're basically adding calcium carbonate to our soils. And the first step that's going to happen is you have the calcium carbonate reacting with carbonic acid in the soil. You get the intermediates of calcium and bicarbonate in the soil. So looking at the clay particles in the soil or humus particles, just oversimplifying what Hai-Ying was showing before, we're basically displacing our hydrogen or our trivalent aluminum, the toxic aluminum, with calcium on those clay particles. And then when we complete the reactions, we're basically ending up with end products of water and carbon dioxide. In the case of aluminum, it's actually forming aluminum hydroxide, which is another form of aluminum in the soil that's not toxic to plants at all. The study we've been doing, I did some earlier studies, which I'm not going to mention today. Tim talked a little bit about some of that work where we were looking at modest rates of lime up to a ton per acre. But I really want to look at larger rates of lime because a lot of the lime requirement tests that we're running suggest that we need about 2 to 3 tons of lime for a lot of these soils. So we selected a number of locations in the Potlatch, Tensed, and Moscow areas. We wanted fields that had a soil pH near or below 5 in the top 6 inches. We wanted some free aluminum in the soils, ideally above 20 ppm. And we wanted them to be uniformly acidic. We applied 1, 2, and 3 ton rates using ground limestone that we sourced from the Camas Prairie. And then we followed these rotations over 4 years. So we're starting into our 4th year. But the intent is these are going to be long-term studies. So to look a little more specifically at our 5 sites, we have soil pH in that top 6 inches that varies from 4.6 in Potlatch to as high as 5 up in 10 SID. You can see the quantities of aluminum from as low as 13 up to 65 parts per million in Potlatch. The CEC was mentioned before by Hai-Ying. The higher the CEC, the more lime we need to increase that pH. So we've got some that are a little bit on the lower side, 11.1. So we don't need as much lime to increase the pH, and as high as 18. So ideally, to reach a pH of 6 in that top 6 inches, we needed about 2.1 to 2.8 tons per acre based on some lime requirement tests that we ran. So this just gives you an idea of the crop sequences we've had at these 5 locations. We limed in the fall of 2016 at 4 of the sites. We added Moscow in 2017, and we've primarily been doing a spring legume winter wheat rotation. So we've basically been following the rotations that the growers have been using at those locations just to simplify management of these trials. So just to show you some data from this last year, we've averaged across all 5 locations, and we've seen an increase in our pH at the 0 to 3 inch layer. And I should mention, back up just briefly, the lime after we applied it was incorporated by cultivation. We cultivated about 5 to 6 inches deep, so most of that lime probably got incorporated in the top 3 inches, a little bit into that 4 to 6 inch layer. But we saw pretty dramatic increases in our lime in that top 3 inches, almost a unit increase with our 3 ton rate. A little bit less of an increase in that 3 to 6 inch depth, but each year we're seeing progressively more improvement in our pH of that 3 to 6 inch depth, and really nothing going on in 6 inches or deeper. But what's really striking is if we start looking at the aluminum concentrations. If we look at the 0 to 3 inch depth, we've gone from basically about 36 parts per million on average down to less than 10 with our 1 ton rate, less than 5 with our 2 ton rate, and basically to the background levels with our 3 ton rate. At the 3 to 6 inch depth, although we haven't reduced it quite as dramatically, there's still pretty significant reductions in the quantity of KCl extractable aluminum in these soils. Just briefly getting to yields, I guess we'll just quickly, in the interest of time, jump to the averages here. So if we look across all 8 site years that we've done, we've seen about a 6 bushel advantage to the 1 ton rate, 9 bushels for 2 ton, and 11 bushels for the 3 ton rate when we look at wheat. We look at some of our alternative crops, and the biggest responses we've seen have been with lentils and peas. Nice incremental increases with lentils. With some of our spring peas this last year, we saw anywhere from a 500 to 800 pound per acre increase in our yields. And just to show you the lentils from 2018, I could see these when I came over the hill over here a half mile away. I could see exactly where I put those 3 ton rates. The 1 ton, 2 ton were a little bit less obvious, but most of the field and the no lime rates were just kind of what we've come to expect of our lentils. Kind of this pale green, didn't seem to look too bad until you look at the 3 ton rates, and it was a stark difference. The plants had a lot darker, vibrant green color to them. The rows were closing in more quickly. There were more blooms on these as they matured, and just a lot healthier looking plant, better weed competition, and so on. So just briefly, I'm going to get to the economics here as I wrap this up. So the way we've been looking at liming, rather than as a production cost where you're going to have a one-time investment, you're going to see returns for a year, that's not what we're seeing with liming. If we put lime on our soils and we put a sufficient quantity down, we're going to be seeing advantages for a decade, 2 decades, perhaps even longer. So we're looking at these as a capital investment rather than a production cost. And we're estimating, and I'm being kind of conservative here with our crop rotations and what we expect from the quantity of nitrogen we're applying, how much more acidification we're going to be receiving, but I'm estimating about a 10-year advantage for a 1 ton rate, about 15 years for 2 tons, and 20 years for 3 tons. And again, I'm trying to be conservative with these estimates, but we really just right now lack the long-term data from this region, so that's part of the point of this study. So basically we're annualizing the cost of the lime. So the cost, this was in 2016 dollars, for the cost of the material, delivery, application was about $87 for the 1 ton, $161 for the 2-ton, $235 for the 3-ton. There was our efficacy, 10, 15, and 20 years for the 1, 2, and 3-ton. Into this calculation, we worked in a 6% discount. So I like to think of this as an interest rate, because you're going to have to, if you're doing this over time, there's going to be interest associated with it. And this we came up with an annualized cost of $12, $17, and $20 over those 10 to 20 year periods of time. If we look at our yields from one of our locations in 2017, we see we had a 6 to 11 bushel increase in yield. The value of that, based on $4.45 per bushel, was $27 to $49. So we're seeing about a $15 to $25 increase in our return by having applied lime to these soils. And if we expand that to all of our sites that we've done so far, and so this is our rates 1, 2, and 3-ton. This is the return over the no lime. And we've taken out, deducted from this, our annualized cost. So this is your return after paying for that annual cost of lime. There's a few situations here where we're not seeing an advantage, but most of the cases we're seeing a positive return from that annualized cost of lime. And if we look at all 11 site years we've done so far, on average we're seeing a $19 per acre increase for the 1-ton, $22 for 2 tons, and $32 for the 3-ton rates of lime. As our crop values go up, these numbers are going to change pretty dramatically. If we had $7 wheat, we'd be paying for this lime application in 5 to 6 years. I guess that's all I have. I just wanted to leave you this photo. This is actually from the Parker farm, just adjacent to where I screened for aluminum toxicity. We applied 3 tons of lime to this part of the field about 3 years ago, and we planted some barley in the field this year. This had no lime, but we did plant across it. The planting went this direction. Just kind of gives you an idea of what we're dealing with and some of the solutions and what lime can do for our cropping system. So.
Thank you so much for the that you